Cool. This talk is about trying to solve a problem that, yes? Oh, thank you. It's about trying to solve a problem that I am sure many of you have encountered before. To explain the problem, let me try to switch to Emacs and not to block the screen here. Ooh. It's going to be a bit challenging. Let's see if I can get this to work. Okay, let's hope for the best. Let me try to make this a little bit larger. If I stand over here, okay, I guess this is visible. So let's pretend that we're doing some programming language meta theory. We have a big, complicated, too small. Let me make this bigger. How's this?
Better.
Better? Okay. Now let's imagine that we're doing some programming language meta theory, and we have a big, complicated inductive definition representing the syntax of our programming language. God damn it. There we go. Right, I guess some of you might recognize this as an excerpt from Iris's heap lang. One is that you have a lot of constructors and a lot of arguments. And let's imagine that for whatever reason you need to define an equality operator for this data type with proofs that it's doing the right thing. How would you go about this? Well, there's a few approaches that are available in standard Coq. One thing that you could do is to define this operator by hand. So here I have a little recursive function that traverses two literal expressions in parallel and uses the equality comparison operator available in ssreflect to compare the arguments of the constructor. Right? With a little piece of LTAC that perhaps you would be able to automate, you can show that this operator is doing what it's supposed to do. If you were patient enough, you could repeat this exercise for all the other types that define the syntax of your programming language. The problem with this, of course, is that it is extremely tedious. You would be implementing operators like this for your whole life and will never get to prove the interesting theorems that you care about. If you don't want to do this, there are other things you could do. You could use Coq's scheme equality command, which generates operators like this for you for free. And this works reasonably well. I think that in terms of syntactic overhead, it's the one that costs the least. The problem with that is that it's not very generic. You might want to implement other type class instances for your data type. Perhaps you want to show that it has a default inhabitant, for instance. And scheme equality cannot do anything for you there. Moreover, this approach doesn't really integrate well with the overloading mechanisms of Coq. So if you print out the term that is generated by this guy for you, you will see, oops, this is a little bit small, so I'm trying to get this bigger. Right. So what you see here is that it's generated equality comparison operators for all the argument types that occur in that inductive. And this, well, if you want to use, say, generic lemmas that talk about equality deciding operators that are available in MathCom, for instance, well, tough luck. You have to essentially define instances for each of these equality comparison operators, and then you get this, but you kind of wish that you didn't have to do that, right? Now, there are some... That one works better. Sorry about that. Let's see if this works. All right. So far, so good. Cool. Long story short, today I am going to tell you a little bit about this library I've been developing called Deriving, which allows you to automate this process and here. So it has a few nice features compared to the standard approaches that are available in Coq. It ships by default with default instances for math comps base type classes, so you can use this to derive instances for EQ types, choice types, count types, etc. But you can extend this, these generic instances to work for other type classes that you might implement. So I implemented, for instance, a type class of ordered types, and I could write my own instance of a generic order type class. And all of this can be done with no custom OCaml code, no plugins. Before telling you how this works, let's show a simple demo. To use deriving, you start by convincing Talk that a given type is an inductive type. So here I have this little declaration that builds in a refi representation of that literal type that defines syntax of literals in my language. I can repeat this for all the other types, going all the way up to the syntax of expressions. You see that right now, the approach that I use for refining these into Coq values is not very efficient. It's using some type class inference in the background, as we will see shortly. But if you wait for long enough, at least eventually this thing ought to terminate and produce a representation that we can use. Maybe. Let's wait. Okay, there we go. Now once this is done, you can write generic dependently typed code that analyzes these refied representations and builds instances of these type classes for you. Here's what I'm doing for the EQ type class for all these expressions. And after this expression stops evaluating, I will have a generic equality operator for the type of expressions in deep lang. And if you print out what comes out of this representation, you'll see that the function looks a little bit weird, not quite what a programmer would write by hand, but it's not so bad, right? So the only weird things here is that you have this dangling true at the end of your logic comparison, and you also abstract over the second thing that you're comparing inside the match as opposed to at the top level of the function. As I mentioned before, this generalizes to other instances, so here I'm defining instances for choice type, count type, and maybe even fin type if your type happens to be finite and doesn't have any recursion. Now, the rest of the talk, I would like to tell you a little bit about how deriving is implemented and how you can use it to write maybe your own type class instances if you care about such a thing. So how does it work? Well, first of all, we have to describe what it means for a type to be inductive. It's a first class definition side talk. And there's some LTAC and type class machinery to automate the process of building this refined representation. And finally, you can use this infrastructure to write generic instances as dependently typed programs. Let's start by talking about how we represent inductive types. If you have read Adam Tabla's Certified Programming Dependent Types book, you might have seen something similar in his generics chapter. Here, I'm representing a non-mutual inductive type as a list of RDs of arguments for each of the constructors of the data type, right? So constructor argument is represented as either being a non-recursive argument, some type T, or a recursive argument. And the signature of a constructor is given by a list of such arguments, and the signature for the entire inductive data type is simply the list of all the constructors that you have for their types. Well, so just to give you an example, suppose that you have a little type of binary trees that is generic. We can define a little signature for this tree type where we have two arities, one representing the leaf constructor, which is empty, has no arguments, and another one representing this node constructor, which has three arguments, two recursive arguments, and one non-recursive argument of type T in the middle. Cool. This signature. So what does this record say? It says that an inductive type is some sort. This is the inductive type that we're representing. And then there's a few things here. We have a list of all the constructors of the data type. We have a recursor for the data type, a destructor, and we have a bunch of equations and induction principles for that data type. What makes it possible for us to define these things inside of clock is its rich type system that enables type level computation, right? So there's a little library of dependently typed combinators that ships with deriving that allows you to, say, express things like a heterogeneous tuple of arguments to a multiple argument function and write a function application that takes these heterogeneous functions and applies them to these heterogeneous tuples. Once you have something like this, you can define, say, the type of constructors for an inductive data type as follows. So suppose they have some signature sigma, and the type T that are trying to prove is inductive. The type of constructors for that data type is simply a heterogeneous tuple of all the constructors of the data type, where a constructor is defined as a heterogeneous function taking arguments according to the arity of the constructor, and the type of the argument of the constructor is simply, well, if it's a non-recursive argument, S, then it's just S. If it happens to be a recursive argument, then it's simply the type T that we're trying to represent. Okay? So just to give you an example, if you instantiate the definition of constructors that I gave to you earlier with the tree signature that we saw, then we'll get exactly a heterogeneous list that we can instantiate, say, with the leaf constructor of the data type and the node constructor. I'm not going to tell you a little bit much about how we represent the other ingredients to representing an inductive data type. If you're interested, you can look in the Coq definitions. But I'll tell you a little bit about how we infer all these representations without requiring any human effort. There's a couple of things that we need to infer when we're using deriving. We need to infer a first-class representation of the type, like we showed to you. But we also need to infer instances, or the type class that we're constructing, for all the non-recursive arguments of the type that we're representing. You see, if we want to define an equality comparison operator for a tree type, and it had better be the case that all the arguments of the type are themselves instances of the EQ type class, and we need some way of inferring this. So how do we do this? Well, as it turns out, all this information, the fact that the type is inductive according to some signature, can be extracted from the eliminator that is automatically generated by Coq, right? If you take the tree rect T eliminator for the tree type, for instance, you'll see that if you look at the proof obligation for the leaf case, should be leaf and not left, you can infer that, well, we have some leaf constructor that takes no arguments, right? And here in the node case, well, by writing the appropriate type class instances, you can traverse this and figure out that you have a node constructor that takes 3 arguments, one of which is recursive. And the reason I use type classes here is that I couldn't really quite figure out how to do this without with canonical structures, because we have to recurse on the lambdas to analyze this list of arguments progressively. Once we do this, we need to prove equations showing how the recursive for the data type reduces. Right? And once again, we can write a little Coq program, big dependently typed program, that produces all the equations that we need. In the case of the tree data type here, we'll get a list of equations saying that, well, if you apply the recursor to the leaf case, you'll simply get the leaf case. And if you apply the recursor to a node, then, well, you'll use the proof for the node case while recursing on the recursive arguments here. And the fact that this is expressed as a conjunction of simple equations that follow by reduction means that we can discharge this proof obligation with a simple invocation of the auto tactic. We don't need an specialized LTAC to prove this. This is the first inference step. Next, we need to show that the argument types for our inductive are instances of the type class that we want to build. For this, I used a little bit of canonical structure inference, right? So here we have, I want to call it a class representation for signatures that lifts the class instances that we have at the level of types. So a signature class is simply a signature. That's the signature they extracted for the inductive data type that we are analyzing, plus a heterogeneous matrix of instances for the non-recursive arguments of that data type. And with a little bit of type class programming, like Gontier and Beta did, you can infer this thing without too much hassle. Cool. How much time do I have?
12 minutes.
12 minutes? Okay, cool.
Including questions.
Yes, okay, cool. So I'm about to wrap up. I would like to finish by giving a little demo of how you might make more advanced usage of deriving by writing your own generic instances. Go back to Emacs here. Okay. So I'll show you how we can derive instances for EQ type, but the pattern is pretty much the same for many other instances that you might want to define yourself. Let's see. So here I'm importing the relevant deriving files, and I am instantiating then a signature instance record for the EQ type class. So there's the equality.sort projection that projects from an EQ type onto type. I'm just defining this notation just to make the development a bit easier to read. Now, ideally, we like to define a function that works more or less like this. How do we compare two elements to see if they're equal? Well, we pattern match on them. We check if their constructors are equal. If they're not equal, then we know that the two elements are not going to be equal. But if they happen to be equal, then we're going to recurse on the list of arguments to those constructors, right? And, well, if we run out of arguments, then we know that the two things are equal. But if we have two elements at the top of the list, then we need to check if they're recursive or not. If they're a recursive occurrence of our data type. If it's not recursive, we're simply going to use the equality operation that we get from the EQ type instance. Otherwise, we're going to perform a recursive call, their function that we're defining, and we're going to recursive the tail of the list of arguments. Now, the problem, of course, is that we can't quite write this function in Coq, so we need to write something else. And deriving comes with a, and the way we do this is by using a different representation of the inductive types that I just gave you. Because using directly the eliminator principle expressed as a dependently typed function with multiple arguments is kind of difficult to do. So we're going to take a more traditional approach where we are morally representing the inductive type as the initial algebra to some functor. So instead of manipulating these multiple argument functions, we're simply going to write the fold using the functor. Concretely, what does this look like? Well,
you had a field in front of
I'm sorry, it's a little bit inconvenient right here. Let me see if I can bring this closer.
field in front of the record lines.
The field in the front of the record.
There's a field commands.
The fair, okay, so this is a simplified definition of what's actually used here. The real definition is this lat one, where I'm instantiating this functor f to be the functor that we get for the signature of the data type that we're using. Okay. So how do we So how do we write this function? Well, here is the code that traverses a list of arguments for the same constructor. And it works by simply calling this arity-rec combinator that allows us to traverse a list of arguments while invoking the appropriate type class instances for the non-recursive arguments. So there's a case for recursive arguments right here and a case for non-recursive ones here. And once you have this, you can define the entire body for the function by using these combinators for the initial algebra, and prove that the function does what you expect it to do using the induction principle for your data type. So this brings us to the end of my presentation. There's a bunch of future work left to do. I'd like to support mutually inductive data types. This, I think, shouldn't be too hard. Doing other things like nested inductives or index families, I think, will be harder. Also, you saw that the inference of the refi representation is not very fast. We would like to speed this up a little bit if possible. And that's it. Thank you very much for your attention.
Okay, thanks. Any questions?
So what about the generation of name of bound variables? Like you get random x something. I think it looked like that in the example. You get, like, it's quite important to actually get like readable things. Otherwise, you get introduction principles completely broken.
Yeah, that's right. Okay, so right now I'm not being very careful about the names that I generate. It would be good to generate more meaningful ones. Yeah.
Any other questions?
I wondered, could you go back a slide, please?
Yes.
If you have an expression type where you can have a list of expressions as an argument, does that fall into the nested inductive?
That's
types
correct.
or okay.
Yes.
And you think that should be possible in the not too distant future?
I think it should be possible, but it might not work out as naturally as for plain inductors, because for those we can just reuse the eliminator that Coq produces. And Coq doesn't produce a useful eliminator for these data types.
Yes, that's what made me wonder about it. But somehow you'd hope the type classes would lead you to a list map. You'd have to declare a list map eq for the equality.
I've been told that LTAC2 has some support for inspecting this information, so maybe with some LTAC code it would be possible to build a better eliminator, but I'm not sure. I haven't thought too much about this.
There's some work in Isabel, I think, where they tackle the same problem with the generic framework, and I've often just wondered if it might apply to Coq as well.
That's good.
Thank you for the talk. I have two questions. So first, you mentioned that you are using a combination of type classes and canonical structures.
Yes.
What is your experience with that? Mine is moderate, at best.
So the only reason for this choice is that I'm more familiar with canonical structure inference, so I implemented everything with canonical structures, but then I had this traversal under lambdas thing that I couldn't do with canonical structure, so I went with type classes there. I wish there were a more principled, faster approach for doing this, and there probably is, but I haven't explored it very deeply yet.
Okay, so going on the binders with canonical structures are just something that people don't know how to do?
Yeah.
Or... Aha, interesting. My second question is about speed.
Okay.
So what is the reason why it took quite a while? Is it a call too simple, or is that something else?
So this is a good question. I haven't investigated this problem very well yet, primarily because I found out this bottleneck when I try to apply the inference to that big data type. But I suspect what's happening is that the heterogeneous lists require the type of the tail to be expressed every time you apply cons, right? And this grows up quadratically with the number of constructors that you have in your data type. The time that it takes to process that thing seems to be growing roughly quadratically, so there might be something to do with that. I don't know.
The quadratic complexity is to be expected, since Coq does not natively support nested matches. But I mean, there is probably like a large constant vector, which you may want to optimize.
Any other question? You have time for one or two more questions?
So you're not covering indexed families, but can the arguments of constructors depend on each other?
No. It's just plain inductive data types.
Okay, let's thank the speaker again.